We just got through talking about the parallels between hydrohalogenation of an alkene and hydrohalogenation of an alkyne. So the next step is to think about the parallels between the hydration of an alkene and the hydration of alkynes. So, like alkenes, alkynes can be hydrated with water in the presence of sulfuric acid. So the reaction conditions are somewhat similar, but there usually is a slight little variation to it, and that is the addition of mercury salts that are used. And they're used to simply facilitate the hydration. The reason why mercury salts are used is because, if you recall, there is similarity between that of oxymercuration of an alkene. Why? Remember when we talk about the hydrohalogenation of an alkyne, and we saw that you can't really form a carbocation, right? Because it's unstable. So we had to kind of speculate that the hydrogen, the proton that's adding to that pi system, is really hovering in between the two carbons. Well, how do we kind of avoid that scenario? We avoid it by using mercury salts, right? Because we know that in oxymercuration you get essentially a hydration and it's promoted by the mercury. So the net result is the same as that of hydrolysis. It's just that you don't get rearrangement with alkenes. So that's kind of the beauty of oxymercuration of alkenes. Well, the beauty of adding mercury salts to alkynes is that they facilitate the transformation process because you have a mercurinium ion as an intermediate instead of this strange hydrogen hovering above the pi system of the alkyne. And so the mechanism is, we're going to be using water, we're going to be using sulfuric acid in the process, right? And the mechanism is going to be the same. We get the pi system attacking the mercury, the lone pair of electrons from the mercury going to the carbon. One of the acetates comes off, right? So you get a loss of acetate, and you end up with the mercurinium ion that has a positive charge. So now water can come in, attack the carbon, one of the carbons, displacing the carbon-mercury bond, and the result is this. And so you get the oxonium ion forming with mercury acetate. And so now all I have to do is simply deprotonate with water, and I get this. So I end up with a mercury salt, which is very similar to what I get in the oxymercuration step, right? Now there is a little bit of difference here because if you recall in oxymercuration, now I have a carbon-carbon single bond and I have this mercuric salt. And so in order to get rid of that mercuric salt, I basically have to add a reducing agent. The difference here is that I still have a pi bond, and in acidic conditions, right? So remember I have an acid present, so sulfuric acid, which is going to react with water to give me the hydronium ion. So I can react that alkene with an acid. And the result is that I get a carbocation. So now I have my carbocation. Notice the carbocation is connected to an OH group. Why is that important? Because I can draw a resonance structure which stabilizes that carbocation and places a positive charge on the oxygen itself. So I'm delocalizing that charge. Now, what happens next is I simply can hydrolyze the mercury acetate off. So I can react that with water, and the electrons from the carbon-mercury bond can simply go in to form a new pi bond and displace a carbon-oxygen pi bond. The result looks like this. So I'm actually not reducing mercury salts to mercury metal in this particular example. I still end up getting mercury salt. So in essence, the mercury salt is a catalyst for this type of reaction. And as a matter of fact, it can go on and react with another alkyne. But the key is that the product that I get is an enol. Now, what is important about an enol? Enols have some kind of interesting chemistry, and we're going to see a lot of chemistry of enols in the second semester. But one of the things that you have to understand is that enols are somewhat unstable in aqueous acidic conditions, and that's exactly what we have here. They're unstable in acidic conditions, they're also unstable in basic conditions. They undergo what's called tautomerization. And in that process, you form a ketone. So, why is that? Notice I have an alkene. In acidic conditions, what happens to that alkene? Well, I can undergo a proton transfer. And when I undergo a proton transfer, I'm going to form a carbocation. That carbocation is going to be, the most stable carbocation is the one attached to that oxygen. Why? Again, because of resonance. So resonance can stabilize that carbocation intermediate, and I get this. Now, a carbon-oxygen bond is very stable, and we're going to see this trend kind of appearing over and over again in the second semester. But because of this, notice I basically have a ketone that is protonated, and now all I have to do is deprotonate that ketone, and I form now my ketone. So I've gone from an enol up above to a ketone. And these two are not resonance structures of one another because in essence I'm moving the hydrogen on the OH to the carbon on the right hand side, right? So notice that CHR is becoming a CH2R, and I'm relocating where the double bond is. That is what is called tautomerism, where you're moving double bonds, but you're also moving a proton from one source to another. So these are tautomers of one another. An enol and a ketone are tautomers of one another. They are in equilibrium with one another in acidic conditions or in basic conditions. And we're going to see that play out later on. But in acidic conditions, they are in equilibrium with one another. The ketone is favored in that equilibrium because a carbon-oxygen double bond is more thermodynamically stable than a carbon-carbon double bond. So the carbon-carbon double bond is more reactive, and it will react to form that ketone. Now, the net result then of the hydration of an alkyne is that alkynes hydrate to yield enols, but they don't then further react to form geminal diols like you would expect in a hydrohalogenation. Instead, the enol tautomerizes to give ketones. So that's an important little twist. Recognizing the similarities between hydration and hydrohalogenation of alkynes. So the first step is very similar, but the second step is quite different, right? So now when I have an alkyne, I react it with water, sulfuric acid, and mercury acetate. I get a ketone. So here I have 2-pentanone. Now what happens if I try to hydrate an alkyne that is unsymmetrical? So here I have my triple bond. On the left hand side I have an ethyl group, and on the right hand side I have a propyl group. Notice here I'm using water, sulfuric acid, and mercury sulfate. again, the mercury, remember, is a catalyst. The mercury salt is a catalyst, so I don't have to use acetate. I could use sulfate. I could use a lot of different salts. And oftentimes you'll see mercury sulfate because you're using sulfuric acid. So in this, if I use an unsymmetrical alkyne, then I'm simply going to get a mixture of ketones, right? Now, how do you predict where the carbonyl is going to go? Well, if I number my alkyne 1, 2, 3, 4, 5, 6, 7, then I can draw that 7 carbon chain, right? 1, 2, 3, 4, 5, 6, 7. And I know that the carbonyl can go on the 3 carbon, so there's the carbonyl, or it could go on the 4 carbon. So I get another ketone in this case where the carbonyl has added to carbon number 4. And so I would get a mixture of products, and this typically is not favorable to get a mixture of products, and therefore we tend to avoid those types of problems. But recognize that if you're given an unsymmetrical alkyne, you will get both both ketones forming.